Hi, welcome to your MECH 200 Statics online classes. Today we're going to start chapter 5 of the textbook, in which we will study the equilibrium of a rigid body. In this first video, we are going to start with the basics on how to represent some key elements of rigid bodies. I hope you enjoyed this class. For this chapter, we have three main objectives to accomplish. First, the concept of free body diagram for a rigid body will be introduced. Next, we're going to develop the equations for equilibrium for a rigid body. And finally, we're going to show how to solve 2D and 3D problems using the equations of equilibrium for a rigid body. Before we start, let's briefly recall the definition of rigid body we saw in chapter 1. Unlike a body that we assume to behave as a particle, a rigid body is considered to be a combination of a large number of particles, in which the dimensions and mass properties of the body must be taken into consideration. However, we will further assume that a rigid body will never deform when external loads are applied to it. Well, that's not quite true in real life, because all bodies deform when subjected to loads. However, for engineering purposes here, we can approximate them as rigid bodies, since most of materials used in engineering, such as steel and concrete, are very rigid under normal operating conditions, and so their deformation is usually very small. This assumption makes calculations a lot easier for engineers. To solve equilibrium problems involving rigid bodies, we can use the same methods of the previous chapter, in which the forces and couple moments acting on a body can be reduced to an equivalent resultant force and resultant couple moment at any arbitrary point of rotation located at point O. For the equilibrium condition, the resultant force and couple moment are both equal to 0, and the equilibrium state can be expressed by this set of equations. We can say that these two equations are not only necessary for equilibrium, but they are also sufficient. These two equations are still valid in a case that, for example, we change the center of rotation of the body to an arbitrary point A, in which we can map out the distance vector r between points A and O. For this case, the equilibrium equation for the couple moment can be rewritten by adding the moment caused by the resultant force about point A to the resultant couple moment about point O, and making this sum equal to 0. As we did in chapter 3 when we studied the equilibrium conditions for a particle, let's start first with the analysis of equilibrium problems in 2 dimensions, in which all forces acting on a rigid body lie in a single plane. For example, consider a car which has a plane of symmetry passing through its center axis. If we pass a cutting line through this center axis, we can consider that the reaction forces on the front and rear tires on the ground and the car weight are symmetrical with respect to this plane, which allows us to solve the forces only for a half of the car geometry in a 2-dimensional configuration. In this arrangement, the weight of the car weighs on its center of gravity G, which will be located at some point in the plane and will have only 2 coordinates. Furthermore, the couple moments generated by the forces will be directed perpendicular to the plane of the page. Now, let's turn our attention to the very first step we have to take before going through the equilibrium equations for any statics problem, which is drawing the free body diagram. You must recall from chapters 3 and 4 that free body diagrams are helpful to identify all known and unknown external forces and moments acting on a body. We have already learned how to draw free body diagrams for particle systems. However, rigid body systems are quite more complex than particle systems. For this reason, a deep understanding on how to draw a free body diagram for a rigid body system is of primary importance. But before talking about how to draw a free body diagram for 2D problems, we have to consider first the different types of reactions that occur at supports and points of contact between rigid bodies when subjected to loads. As a general rule, a support prevents the translation and/or rotation of a body in a given direction by exerting a force or a couple moment on the body in the opposite direction. For example, let's consider three different ways in which a horizontal beam is supported in its end. One method is symbolically represented by a roller or a cylinder, and it prevents the beam from translating only in the vertical direction. That's why we have the vertical reaction force F here. Despite the restriction for vertical movement, the beam is free to move back and forth in the horizontal direction. If we also want to restrict the movement of the beam in the horizontal direction, then we can apply a pin connection in which the pin passes through the hole in the beam and two leaves which are fixed to the ground, like in this configuration right here. As a result, the pin connection can prevent both vertical and horizontal translation, and the two reactive forces Fx and Fy appear in the support. However, the beam is still free to rotate about the pin axis in any direction angle phi. The most restrictive way to support the beam would be using a fixed support, as shown here. This support will prevent both translation and rotation of the beam in all directions, and as a consequence, one reactive couple moment and two reactive forces in the x and y direction will take place in the support. We have several important types of supports for bodies subjected to coplanar force systems, and I'm going to list here the 10 most used ones. Remember, you don't need to memorize all of them. Just carefully study each of the symbols used to represent these supports and understand the types of reactions they exert on their contacting members. These supports were extracted from table 5.1 of the textbook, and you can always have it in hands when you are solving problems. The first type of support is the cable connection. As we already studied in chapter 3, this type of connection will generate only one reaction force, that is the tension force through the direction of the cable. This tension is the only unknown that must be determined in the problem solution. The second type is the weightless link, which is a solid link between the leaves and the member to be connected. This connection will cause only one reaction force, which can act in both directions along the axis of the link. The third type is the roller connection, in which the only reactive force acts perpendicular to the surface at the point of contact. Therefore, the connection can slide over the surface with no restrictions. The fourth type of connection is the rocker, in which there is only one reactive force that acts perpendicular to the surface at the point of contact. The fifth type is a smooth contacting surface, in which again, the only reaction force is the one perpendicular to the surface at the point of contact, and acts to restrict the movement through this direction. The sixth type of connection involves a roller or a pin in a confined smooth slot. In this type of connection, the pin or the roller is free to move along the slot, and the only reaction force acts perpendicular to the slot. The seventh type of connection considers a member pin connected to a collar on a smooth rod, in which the only reaction force acts perpendicular to the rod, and the member is free to rotate about the pin and slide along the rod. The eighth type involves the connection between elements using a smooth pin or a hinge to restrict the translation movement in any direction, causing a reactive force that has two components, one in the x and other in the y direction. However, the connecting member has some freedom to rotate along the pin axis, depending on the configuration of the system. The ninth type of connection considers a member fixed connected to a cooler on a smooth rod, in which the restriction causes a reactive couple moment and a reactive force acting perpendicular to the rod. And finally, we have the most restrictive type of connection, which is the fixed support. As we saw in slide number 5, this connection causes a couple moment reaction due to the rotation restriction and a vertical and horizontal force reactions due to the translation restriction, which can then be used to calculate the resultant reaction force and its direction angle phi. Typical examples of actual supports can be found in the cable exerting a force on the bracket in the direction of the cable, which falls into the type 1 cable support connection, the typical pin support of a beam, which falls into the type 8 pin support connection, and the floor beams of the building here that are welded together and form a type 10 fixed support connection. Now that we have everything we need to get started with rigid body analysis, let me give a few tips on how to come up with an idealized model that is a good approximation of the actual situation. To do this, the knowledge about material behavior and dimensions of the objects are very important. But especially for these problems, careful choices should be made on what type of supports to use. In any case, this selection process requires both skill and experience, but with enough practice, you can get both. Let's consider this actual situation, in which a steel beam is used to be the support of 3 roof joists of a building. For the force analysis here, it is reasonable to assume that the material, steel, is rigid enough since only very small deflections will occur when the beam is loaded, and then we can apply the rigid body assumption for the beam. Now, let's analyze the supports. For this support at A, a bolted connection will allow for any slight rotation when the load is applied, and so a pin can be considered for this support. Now, for the support at B, we realize that a roller can be considered, since this support offers no resistance to the horizontal movement of the beam. Finally, we can calculate the magnitude of the 3 joist loads on their locations along the beam length by following some building design codes. In situations like this, the weight of the beam is generally neglected if it is small compared to the load that the beam supports. As a second case, let's consider the lift boom shown here. By inspection, we can see that it is supported by a pin at A and by a hydraulic cylinder BC, which can be approximated as a weightless link. The material can be assumed rigid, and having its density known, the weight of the boom W and the location of its center of gravity G can be determined. Then, once the designed load P is specified, this idealized model can be used for the force analysis, giving the average dimensions, not shown here, to specify the location of the loads and the supports. Let's establish now a simple procedure of analysis to construct a free body diagram for a rigid body, or any groups of bodies considered as a single system. We have to start by drawing the outline shape, in which first, we have to isolate the body from its surroundings and connections by removing all supports from the body. Then we are ready to draw a simplistic sketch of the outline shape. The next step is to identify all known and unknown external forces and couple moments acting on the body. They are generally caused due to applied external loadings, reactions occurring at the supports or at points of contact with other bodies. For this one, always refer to the support elements shown in slides 6, 7, 8, and 9 of this video presentation. And we also have the weight of the body, which will always act at its center of gravity. For the problems in this chapter, the location of the center of gravity will always be given in the problem statement. Later in this course, we will learn how to determine the center of gravity of a body, considering its mass distribution and geometric properties. Lastly, we have to label each loading and give the appropriate dimensions by first establishing the direction of the coordinate system axis and then labeling the magnitude and directions of the known forces and coupled moments and the dimensions given to calculate the moment of forces. For the unknown forces and coupled moments, we have to use letters to represent their magnitudes and direction angles, in which initially we are free to assume their direction and check them after the calculations are done. Now, let's work on one example. In example 5.1, we have to draw a free body diagram of the 100 kilograms uniform beam shown in the figure. To solve this problem, we have to consider the procedure of analysis described in slide 11. First, we have to isolate the beam from its connections with the wall and sketch a simple outline of its shape. Next, we have to identify and show in the free body diagram all forces acting on the beam, starting with the vertical load of 1200 newtons applied at a distance of 2 meters from the wall. Then, by analyzing the support at A, which is fixed, we have three reactions of the beam: the forces AX and AY, and the couple moment MA. The last force to be identified is the weight of the beam, equal to its mass multiplied by the gravitational acceleration, which acts through the beam center of gravity G, located at half of its length, since the beam was assumed to be uniform. The free body diagram is now ready to be used for the application of the equilibrium equations. Now, it's your time to go through examples 5.2, 5.3, and 5.4 of the textbook on your own. Before you do it, carefully review the procedure of analysis provided in slide number 11. And with that, we have finished the first part of chapter 5. Thanks for watching, and I'll see you in the next video.